we've got a lot to cover, and I am committed to doing a better job of taking this significant amount of information and compressing it into 30 minutes of hopefully very useful and reviewable content and for our customers. So, again, the reason that we are putting these together is we want to be adding value to our customers all times. That is our mission at CapEx. We want to continuously be adding value to and for our customers, helping to build our manufacturing industry and community into a more knowledgeable community, specifically around the products that we sell. We're also going to be doing a lot of work in the area of how to grow your career. If you are a manufacturing engineer, how to grow yourself in your organization and then grow into potentially, other organizations or other roles that you might desire. We're going to talk about creating the ultimate request for quote. So what kind of information do machine builders, or are they looking for when you create a request for quote, and what's some of the CYA content that you need to make sure you have in your RFQ. We're going to talk about capital equipment project management, some of the fundamental aspects of managing a capital project in an efficient way, and again, holding suppliers accountable, and then how to get traction internally to receive the support that you need to execute a capital project. So we've got a number of different ways, again, that we're just trying to pour into the folks that are at home or not working, or working, but working from home, but able to join in and learn with us. So that's the mission that we have here at CapEx. So we represent ATC Automation out of Cookeville, Tennessee. Just hop through what we do for CapEx. We're specifically in North Carolina, South Carolina, and Virginia. That is the area that we are focused on for supporting ATC Automation. We represent some great companies here. 85% of their business is with repeat customers. That's a key number in the automation world. There are a lot of dead bodies out there as it relates to projects that failed, and companies did not support those projects after they failed. So ATC takes a lot of pride in following through. Even not every project has been amazing, but the projects that aren't amazing, we continue to support and work shoulder to shoulder with customers so that they do come back. And that's why 85% of the business we do year over year is with repeat customers. Cincinnati Test Systems, been with these folks for a long time when they weren't so big, but now they are the largest leak test company in the world, thanks to obviously their efforts, their technology, and then their growth through acquisition and just new product introduction. So wonderful company. And that's, in the 20 years of working with them has allowed me an opportunity to learn about what we're going to talk about today, which is the fundamentals of leak testing. Duquesne Plastic Joining Systems, joining technologies. They are a global and diverse plastic welding, plastic joining company, spin welding, hot plate welding, ultrasonic welding, infrared welding, laser welding. They are all things plastic joining technologies. Symmetric out of Ottawa, Ontario, a part of Cincinnati Test Systems, high-speed in-process test and data management. So all things data as it relates to trying to pull in all of the dissimilar data from torque guns, leak testers, press systems, to integrate that data so that it actually has a level of value for your process so that you can be more predictive and build a better product for your customer. And then Keller Technologies right here in Fort Mill, South Carolina, comprehensive industrial air filtration, wet as well as dry filtration technologies for industrial applications. All right, so we're going to hop into the fundamentals of leak testing. First thing we need to know with regards to leak testing is everything leaks, everything. So if you have a jar of peanut butter and you flip that jar of peanut butter upside down, nothing falls out, well, unless some of the oils from the peanut butter have accumulated, but nothing falls out, right? So we say, gosh, that's a big hole in that jar, but the product that we're trying to retain is not leaking. But if it was any other media in that jar, it would leak. So my point with that is to say that when you have a container that's supposed to retain some type of media, whether it be a fluid or a substance or a powder, or maybe it's to keep things from ingressing in. So maybe it's to keep moisture and dust from ingressing into the product. Just because so the idea is that it doesn't leak whatever media that you're trying to prevent escaping. So the peanut butter jar has a big hole in it, but technically it doesn't leak because the media that we're trying to retain in that jar is not leaking. But obviously anything else, you put water in there and you flip it upside down, it's gonna leak. So, but if we put a lid on it, then turn it over and it doesn't leak, then that is the result that we're looking for in not allowing that product to escape. So what is a leak? So a leak is, from a Webster's definition perspective, it's a hole or permeation. That's what we want to think of as it relates to our parts. But pass through a small hole or crack in a retaining or excluding wall. So yeah, it's technical to have a small hole or crack through which something can pass. So that's a leak. What we're concerned about, what we're interested in, is the leak rate. So the mass of material invading, that's the ingress that I was talking about. So if you have an electronic control module, as an example, that is typically a sealed unit, and you don't want dust or water ingressing or invading into that ECM module, or escaping. So in the case of like the peanut butter jar where we get the lid on it, we don't want the water to escape out either. So at any given flow over a given amount of time, right? So that's how we determine a leak rate. We have a mass over time. So the reasons that we leak test, again, this is the fundamentals of leak testing that we're talking about here. So we want to ensure parts function as designed. We want to reduce overall waste and scrap. So that means that we leak test a casting after it's machined prior to assembling it to a transfer case, as an example. So we would want to test those products so that when they got assembled onto the transfer case, if the transfer case was leak tested and it rejected, then you have to disassemble it because the housing that you used leaked. So it makes sense to leak test that ahead of time so that you don't have unnecessary cost in scrap associated with assembling products that are leaking. So you can evaluate that ahead of time and save yourself problems down the road. You want to improve reliability and improve reliability and reduce liability. And really the result of that is the next one, and that is a higher, greater customer satisfaction. Maybe you want to protect the environment. So one thing we don't think about are those big transformers that are on poles, on the telephone poles. That has some pretty nasty stuff inside of it. So we don't want that leaking out into the environment to potentially cause problems there. We want added process control, and then we want early detection of problems and challenges. So if you are testing a product and there's some type of defect or a fault or problem in your manufacturing process that is making multiple parts one right after another that are bad, if you have the opportunity to detect that early on, then you don't produce thousands of parts that are actually bad because of a manufacturing issue. So early detection allows you to correct problems over the long term. So causes of leaks, and we welcome questions along the way. Chris is helping to curate some of that dialogue. If you have a question, just throw it into the chat box and we'll try to get that addressed as they come up. So definitely, this is for you, this is for our customers to help increase your knowledge of leak testing and how to apply these different technologies. So causes for leaks, we've got defective welds, brazing joints, improper seating of components. So you pressed a seal in, you didn't press it all the way. Maybe we didn't torque the bolt properly, so it's allowing fluid to escape or air to escape. Missing components, gaskets Poor surface finish, that's a common problem and a challenge all in itself. And then machining defects. Leak paths. Now, this is the trickier aspect of leak testing. Most of the leak paths that we see are as a result of the torturous path. So the leak starts here, but goes up and down, up and down, up and down, and it ends up coming out somewhere completely different than where it originates, as far as, going from inside the part to escaping the parts. That's very common. We talk about the torturous path if we think of aluminum die-cast components. So as we die-cast, oftentimes, if there are air pockets or different issues that result in porosity for aluminum die-cast components, then they create a torturous path. So I think of this too as, I don't know if you've ever had a leak, if you've got a sprinkler system, or if you've ever had a leak in a pipe coming into your home. You'll have water coming up in one area, you'll dig there, but the reality is the hole is actually somewhere 3 feet away from where you started digging. So you end up digging up your whole front yard as a result of not being able to really trace that. So it's a torturous path, right? As it comes up to the surface, it is not coming directly or straight up. It's it's got some resistance, so it's just following the path of least resistance to the top. And that's what we all do, really. Follow the path of least resistance. So correlating leak rates, really important in determining the leak rate that we should use for a particular product. The most common question that I get is, what leak rate should we use? And that's these are some of the criteria that we would utilize in trying to understand what is an appropriate reject criteria for your particular application. So these are the things to consider: factors that influence flow and the correlation of flow rates between different fluids, gas, and liquids, right? So that's often what we're using a gas media, air, generally, if we're talking about pressure decay or mass flow, or even helium, which is a gas, or hydrogen. So we are using a gas, and maybe we're trying to retain a fluid. So in the case of a gas tank, we got gas that we're putting into this. We don't want it to leak gas out, but we're using helium technology to test that as our medium. So what is the correlation? How can we correlate between those two? That's a very common question that we get, because most of our customers are not trying to keep air from escaping. They're trying to keep some fluid, whether it be oil, radiator fluid, from escaping their products. So the pressure is very important. The temperature of the fluid that you're trying to retain is important. The viscosity of the fluid, obviously, gear oil is going to be much more, have a much higher viscosity than motor oil. So understanding those two, and then that's going to change as well depending on the temperature of the fluid when it is in operation. Surface tension of the fluid, very important to understand as well, because depending on the surface tension, it might not push through that tortuous path. So that's an important thing to keep in mind. The hole size is something else that is important. Hole size and surface tension, those two kind of work together. So we need to understand those, and then the path, the leak path length, and then the leak path characteristics, also very important as well. So correlating leak rate. So the good news so let's talk about bad news first, I guess. Difficulty, if not impossible, to precisely correlate actual leak conditions with fluid compared to a gas or medium technology, due to the typical turbulent or non-laminar flow of most leaks. So it's highly independent or dependent on the leak path itself. I showed that tortuous path. That top path was very easy, right? So air, goes right through. It's square on both sides, but the normal or typical path is everywhere, right? So the leak path itself is very determinant in the actual part leaking. So the good news is that the air molecules have a much lower viscosity than water, as an example. So air is much more likely to escape a part than the fluid, so the fluid like water. So I think it's at least 16, what does it say here? 16 to, so leak much faster, I'm sorry. So at least 16 to 58 times higher that we're going to leak air. So again, that's why we want to use air as a medium, or helium, or gas technology as the medium for our application, so that we have a greater chance of catching the bad part. Conservative correlation, we learn with experience that is at least 85 times higher flow with air than with water. So even a greater ratio, the higher the viscosity, the higher the ratio, like ATF fluids. So here is the very complicated formula that we would utilize, that we say is plus or minus 50%. That's why we say it's very difficult to correlate a fluid leak with a gas leak. So in my experience of being a part of leak testing for the last 20 years, the empirical evidence of actually testing and identifying parts that are good versus identifying parts that are bad, and then understanding the leak rates of the bad parts and the good parts, and then putting a safety factor in is how most of our customers develop a reject criteria, really through the product development effort. So there's a lot that goes into the formula, and much of it is subjective. So that's why that formula is not very reliable. So expressing a leak rate, when we express a leak rate, is typically determined by measuring either a pressure loss or the volume of substance flowing from a hole or orifice over a period of time. So typical pressure loss, we use PSI, Pascal, megapascal, inches of water column, atmosphere. You can read the rest. I don't need to read those to you, but mostly we see, especially nowadays, so it depends too if you're a European company, but most US-based companies are using PSI, pounds per square inch. And then some of our European customers, especially those from Germany, they like to use Pascal, or in some cases millibar. But most often we are seeing the PSI as the unit of choice. The typical volumetric measurements are standard cubic centimeters or liters. So standard cubic centimeters or liters, and then typical times, of course, seconds, minutes, and hours. So the common units, so for airflow technology, that's pressure decay, mass flow, vacuum decay, differential pressure decay. So any air leak test technology, typically we will use standard cubic centimeters per minute, or the abbreviation is SCCM. For tracer gas technology, those are technologies utilizing helium or hydrogen as the gas that we are detecting. So that would be standard cubic centimeters per second. Typically, those are much lower leak rates that we are looking to detect with those technologies. So when we talk about standard conditions, that's the standard in standard cubic centimeters per minute, are 68 degrees F, and we use atmospheric pressure as the baseline, 14.696 PSI A absolute. So what that would typically look like, I'm sure you all have seen this if you are part of leak testing. The normal display is 12 SCCM at 25 PSI G would be a typical expression of a reject rate. Something else to understand, this is another common question that I get, is a customer will say, well, if I'm leak testing a part at 50 PSI and it leaks, my reject criteria is 10 SCCM at 50 PSI, can I just increase my pressure and use the same reject rate? So let's say they want to increase it to 100 PSI. but still use 10 SCCM. And they, of course they can, but the reality is that test is twice as stringent as the test that they were originally running at the 50 PSI, because pressure and leak rate are correlated, as you can see here in this graph. So as we increase the pressure, the flow rate increases in proportion to that pressure. It's not exact, but if we are going to generalize, it is a pretty linear path. So test pressures. So once the leak limit is established, so that's the flow limit that we're talking about, we need to define the highest pressure the product will see during operation. So we need to understand what pressure is your product going to see during operation. And that is the test pressure that would be ideal for the application, because we want to test it at a given pressure. Now, there are many things that go into determining that level of pressure. So if your part can see 1,000 PSI, as an example, we want to probably pull that back, because they're testing at 1,000 PSI is way different than testing at 500 PSI, way different than testing at 200 PSI, way different than testing at 100 PSI. So from a safety perspective, there can be a number of things that that will impact the application. So the higher the test pressure, the more attention we have to safety, right? Guarding, you've got essentially a bomb. If you're pressurizing a part to 1,000 PSI, you've got a bomb. And if it has a crack in it, if it explodes, you know, if we pressurize this coffee mug to 1,000 PSI, it's going to explode. And when it does, it's going to create a lot of problems. So safety, guarding, big consideration when we're using higher pressures. So it could result in thermodynamic issues. So meaning that there's a lot of energy. We talked last time about pressure decay, how the energy of the air, because it's compressed, those molecules are rubbing together, that creates heat. We are taking that compressed air, we are allowing it to expand and then contracting it when we pressurize a part, right? So it goes, there's no pressure in the part, or it's atmospheric pressure. So it's 14 PSI essentially in the part. And then we open up the pressure source to pressurize the part to our test pressure. So it's going to expand as it goes in. And then once again, it's going to collapse back down in order to achieve that 1,000 PSI. That's that thermodynamic challenge that we have when we're testing at those higher pressures. It causes, so as we have to pressurize our cylinders to seal a part, that can cause seal creep. We talked about last time how seal creep will result in a change in the volume of our part, and anything that affects the volume of the part under pressure is going to change the pressure in the part. So we are essentially measuring pressure change, and anything that affects pressure change in our part is going to affect our repeatability and reliability of the test. So we want to minimize that, or consider that when we're thinking about our test pressures. And then of course we're going to deform the part if we are testing a plastic part, or if we have to put too much pressure to seal on a part, we can deform it. So we got to be cautious of that, take that into consideration when determining the pressure at which we want to test our parts. So it increases the tooling cost, the larger cylinders, maybe you got to go hydraulic instead of pneumatic. So there are any number of challenges that can come in when we increase the test pressure. And so it could also approach or exceed the plant supply pressure limit. So I've seen that many times in my career where we've got to test a part at 250 PSI, but of course plant air pressure is 85 to 95 PSI. So we have to put a booster on the test system. All right, I know I'm rifling through this quickly. How am I doing on time? 28, so I got 5 minutes. Let's see how we can do here. All right, leak test measurement. So a leak test measurement is the measurement of a change of a product, of a production part that relates to a leak. Pretty straightforward, right? So the leak test measurement is the measurement of a change of a production part that relates to a leak. So we're correlating that back to typically a calibration, right? So each leak test technology has variables that affect the capability of this measurement, whether it be mass flow, pressure decay, differential pressure decay. So there are all different variables that we need to consider when we are looking to apply the appropriate technology for our application, because that's what we always want to do. We've got a myriad of options for utilizing technologies. The goal is to, what can I use for my application that's going to produce the most repeatable part, most repeatable test results in the shortest amount of time. That's always our mission. So the key to repeatability and accuracy is mitigating the measurement of variables that are not associated with a leak. So that's the noise, that's the temperature effects, that's that seal creep that we have to take in mind or keep in mind. Sometimes in some facilities, I'll see a cylinder that is pressing down, it's sealing on a part, and the operation next to the station that's doing the leak testing has a big air gun or something that draws down the test pressure or the available pressure for pressurizing that cylinder, and that cylinder backs off just a bit. It burps as a non-technical term. And in doing so, if it does that during the test, it's going to cause a reject. It's going to cause a fault. And those are really challenging situations to track down and identify the problem. So it's important to isolate the test pressure. We can use accumulators on our test systems. That is ideal as well. So factors affecting the leak test. We talked a little bit about this the last time as well, but stability of the part under pressure. How stable is it? What temperature impact, right? We talked about that as a major component of a variable is the temperature, the elasticity, porosity in the part volume is very important as well. The seal and fixture design, extremely important if we want to have a repeatable leak test system. Part variation, how different, is the volume significantly, does it vary from part to part? And if it does, using pressure decay technology is going to be a challenge, right? Because pressure decay is a volume dependent test. So in that case, we might want to consider using a technology such as mass flow, which is not a volume dependent test, depending on which conditions we utilize mass flow technology. So the cycle time is important, test pressure is important, the environmental conditions, are you in a very dirty, moist environment? Moisture has a significant impact on the repeatability of the leak test. And then, changing temperature. Are you next to a bay door? So I know in Michigan, when I was up there, we had problems in the winter. We'd open up the door, and if there's a leak tester anywhere near that area, the sub-zero air is going to rush in, and that's going to affect our repeatability of the leak test because temperature has a major effect on air pressure, right? So device sensitivity is going to be important, especially depending on the leak rate that we're looking for and how do we want to calibrate the part. Temperature sources of variation, HVAC systems, operator fan. So if you have an operator fan, so let's say you're testing radiators as an example. So you're testing a radiator. You don't want essentially water to leak out of that radiator. The radiator is made to dissipate heat. So you've pressurized your part. You've got a test going on, and there's a fan that is blowing air across the radiator. Well, what's going to happen? Well, inevitably, it's going to cause pressure fluctuations inside the part because the temperature, the part is made to dissipate heat. So it's going to cause some significant challenges with regards to testing a radiator as an example. The shipping bay doors, as I mentioned earlier, environmental temperature changes. So you got a facility in the morning, it's cold. In the afternoon, it's smoldering hot. Working through those challenges. We also have part-to-part temperature variation. So we talked about washers, upstream washers. So you're washing a part, it comes out. Typically, part washers have heaters, so the part is warm. So we need to try to cool the part before we test the part so we can have a more reliable leak test. So test part location prior to leak tests is an important consideration for repeatability. Part handling, is it automatically loaded, manually loading? Because our heat from our hands will impact. So if we're holding on to an aluminum part, waiting to put it on the leak tester, we actually transfer thermal change. There's a thermal exchange, right? So from our hands into the part, and it matters. This technology is extremely sensitive, and all those things need to be taken into account if we want to build a reliable and repeatable system that is not a great big pain in our ass every day. You know, hey, come down here, this leak tester is broken. Hey, come down here, this leak tester is broken. If you've been involved in leak testing, you know that that is a potential and just really challenging to allow you to move forward in improving other processes. So supply air is important. I mentioned an air accumulator can be a helpful thing, and then air usage on test system airline leg. So if you have that test system and you run a product over here and it draws down on the available air to seal on your part, again, that's going to cause variability that's very challenging to track down as a problem. So we talked about too the adiabatic effects. That's that temperature. So the temperature of the air when it is in your facility, obviously heat rises. So the air lines are typically up near the ceiling. Well, that air, of course, in those lines is warmer than the air down below it. So the temperature of your part is going to be ambient. You put that on, and then you take this hot air that's above, and you're pressurizing your part. So again, just another consideration in thinking about how to develop a repeatable test. All those things matter. They may or may not be something that you have to address, but they are definitely components that affect the product. So I'm gonna hop through some of these. Man, 1202. Here's some things to consider with sealing design. We want to have these are stoppers right here. So these prevent the product from continually squishing into the part. So we want part stops to minimize travel, so we don't continually extrude the part into the seal. Very important. Cylinder size, fluctuating air pressure lines, durometer of seals. We want to avoid the false rejects and false accepts, right? We've talked about this. If you've been around for any amount of time, we don't want to use push locks specifically on the test side of a leak test. So here we have a C28. It's okay to use push lock fittings over here. This is where we are pressurizing the part. So on the left side of this, right underneath where it says liner 1, this is where we are pressurizing the part. Over here, this is where we're pressurizing our test instrumentation. So this is the pressure supply, right? So we don't care so much if it leaks there. Obviously, we don't want to just waste air, but it is something to consider. And then over here, we are pressurizing the part. So this is part of our test circuit, and it is important that our test circuit does not have leaks, because obviously you can't build a repeatable test if the test circuit is leaking. So that's why we recommend these ferrule style fittings. Very good for creating a robust leak-free connection. We also recommend that you use Nylaflow style line. So that's a nylon based tubing to minimize the expansion, right? So if you're using this thin wall PVC type tubing and you pressurize it to 50 PSI, the line is going to swell. And we know that that swelling, as it tries to contract and come back to its normal state when it is not under pressure, that's going to create pressure fluctuation. And remember, our instrumentation is measuring pressure change. And any pressure change, anything that affects the pressure change or appears as though it is a flow in or out of the product, is going to affect the repeatability of our application. Porosity, flexible parts. We talked about part volume, how that can have an impact. Moisture is an issue. Debris on the seals, that is a common problem if you're in an industrial environment, specifically for a foundry, as an example, right? So you've got a lot of aluminum chips that are floating around from the trim die system that you're using, and those can end up on the leak test or the seals and cause some problems, and you don't have a repeatable test. Obviously, if that's going on, that can cause some variability. And then, part debris. So that debris that we have in the part, if it's a plastic part, as an example, that plastic dust can get sucked into the instrumentation and cause some problems. So in that case, we may want to use an external exhaust valve to minimize the amount of air that is escaping the circuit, the test circuit, back through the instrumentation. Here's some moisture study, and we'll get into all these details. I do want to hit on the fundamentals of leak testing as far as the different types of leak testing. So here are the various types of technology. Obviously, the most basic is the dunk test technology. We've got the airflow measurement techniques, pressure decay, vacuum decay, differential pressure decay is becoming a more and more common test. Pressure loss, so that's just a delta P, very straightforward type of test, no calibration typically. Pressure loss, so that's a slope, right? A delta P over a delta T, so that's a slope test. And then mass flow or differential mass flow are the common airflow technologies. We also have tracer gas techniques, so that's handheld sniffers, tracer gas accumulation, which is essentially a closed system with a sniffer to sense any tracer gas technology. So that's a helium or hydrogen as common tracer gases that we would utilize. And we also have the hard vacuum leak test technology that you would utilize for those lower leak applications like fuel system, high pressure fuel rails, injectors, gas tanks, air canisters for your airbags. So you've got those canisters are important to test as well. So each technology has unique sensitivity challenges. Some are much more robust as it relates to environmental conditions, but are much more technical as it relates to the ability to get it to function all the time robustly. So there are trade-offs with each of these technologies. So we want to, again, evaluate what is the necessary reject criteria for your application. Sometimes, I'll get a customer will say, especially a new customer that's never really gotten into leak testing, they'll say, well, it can't leak, the part can't leak, Russ. So, well, that's, I understand that, but what, there's got to be we know everything leaks. So what is a reasonable accept reject criteria for your application? So, well, Russ, it can't leak. Okay, let's look at it this way. What you're saying is that you need to manufacture a 1-inch square, 1-inch cube, and it needs to be plus or minus nothing. So when you say a part can't leak, that is equivalent to saying that you want to manufacture 1,000,000 parts, 1 inch by 1 inch by 1 inch, plus or minus nothing. Now, we all know that it is impossible to produce millions of parts that are exactly the same. Otherwise, if it wasn't nearly impossible to do that, we wouldn't have tolerances. And so what you do when you determine an accept reject criteria is you're essentially establishing a reasonable tolerance so that you aren't rejecting good parts and you aren't accepting bad parts. We want to find that balancing point, that fine line between accepting and rejecting, because if we just go to the extreme, then we're going to reject parts and we're going to make it very difficult to produce product. And obviously we're all in business from a manufacturing perspective to produce product to ship to our customers. So we got to keep that in mind. So there's the dunk test technology. We talked about vacuum and pressure decay the last time. Sensitivities down to about 10 to the minus 3 standard cubic centimeters per second. Flow test technology, we're going to be talking about that here next week specifically. So we got the sniffer technology. So you pressurize a part and you essentially use a helium or tracer gas sniffer and sniff the leak points, potential leak points of your product. You see the sensitivities 10 to the minus 4. So we're getting a little more sensitive as we move down this list of technologies. The gas accumulation. So this is where we would put a part inside of a chamber, and then we would, again, like I mentioned, put a probe essentially inside that chamber, pressurize the part, and any gas that escapes, any of the tracer gas that escapes, we're going to detect that leakage, and then we'll correlate that to a flow rate. Sensitivity down to 10 to the minus 1, so not cc's per second. Not the most sensitive or ideal, but it is a method that is pretty darn robust. And then we've got tracer gas utilizing clamshell technology. So we introduce a nitrogen shield essentially around the part that makes it very clean for being able to detect finer levels or lower levels of helium or tracer gas escaping the part. So that's 10 to the -5 standard cubic centimeters per second. And then we get down to the most sensitive, most challenging type of technology, which is the mass spec technology. Now, I love mass spec technology because it eliminates all those problems that we have with temperature and part flexibility and part configuration and volume change, all of that. It doesn't matter for a hard vacuum mass spec system. However, there are many other considerations and challenges associated with this technology because we've got high vacuum pumps. We've got to have sealed chambers. We've got to have much more sophisticated control mechanisms on the system to prevent damaging of the pumps themselves, to prevent operator challenges, and can be difficult to load depending on the size of the part. So there are lots of considerations when using this technology, but it is an extremely effective technology for detecting very small leaks. Calibrating questions. Okay, so I want to skip to, all right, here's what we got coming up. We got mass flow on the 29th. We're going to be talking about creating the ultimate RFQ. I mentioned that on May 6th. We're going to talk about growing your influence as an engineer on May 13th. And then we're going to talk about AI in modern manufacturing on May 20th. I got a guest that's going to join for that, and probably have a guest on the 13th to help with some of that communication. So how did I do this time? A little bit better. 12-12. Any questions, Chris, that came up in the chat box? It didn't look
no questions at this time, but obviously if there are, feel free to send those in the chat, and we'll be glad to answer them. If you think of any follow-up questions, feel free to email us, and we will be happy to get back to you or consult with you. Thank you.
No doubt. Yeah. Thanks, Chris. So thanks everyone. Again, our mission is to pour into you, help you be better at applying the different technologies that we are experts in. Now, these guys are all experts in utilizing this knowledge and technology. Mike here in South Carolina, Chris is up in Eastern North Carolina and Virginia, and then Adam is over in the Western North Carolina in the upstate of South Carolina. So appreciate each and every one of you. Let's see here. I'll stop share. So again, there were no questions came up. All right. Thanks everyone. I know that was a lot of information that was thrown out there in a very short amount of time. So appreciate your attention. And again, we welcome any questions that you have in applying this or any leak test technology. Thanks so much. We'll talk to you soon.